Okay, so there are basically there are a few types of problems that you guys might need to solve for today's work. And the first kind is basically just using rough start is basically just using Hooke's law. So using that F spring equal to negative kx. Again, remember that our k is the spring constant, x is the displacement. Spring constant, again, is how stiff this spring is. So the spring in the suspension of a car is really high because those springs have to be really stiff, and a spring in like a ballpoint pen or something would be a lot lower. X is the displacement, which just means how far are we bringing our spring from its equilibrium position, like its natural stretch length. And let's say you are asked for, or let's say the information that you're given is that spring force, or maybe the force that we're applying, again, those should be equal in magnitude. Let's say it is 300 newtons, and let's say our K is 10 newtons per meter, and we're being asked to find X. It's pretty much just going to be a plug-in force. So I'm going to take this 300 newtons, plug that in for our spring force, take the K, 10 newtons per meter, and plug that in for our spring constant. And so the algebra on these problems is actually relatively straightforward. We would just be left with our X there, and we would have to divide both sides by whatever is next to our variable we're trying to solve for. So we have to divide both sides of this by 10. We would end up with an X equaling negative 30 meters. And you could solve for any part of this equation that way. So you could imagine a situation where if we're given maybe a spring force and a displacement, we could even solve for the missing spring constant. If we're given both our spring constant and our displacement, we could figure out what force would be required to achieve that displacement. So you could use sort of all parts of this equation. You could solve for any different part of it. That's the first problem type that you could sort of be asked at this point that shows up on this problem set. The other types of problems are really similar to what you guys were doing yesterday when you were doing investigations of what happens if I double a spring constant, or what happens if I double the amount of force that I'm exerting on this thing. So for example, let's say you're told that you're not usually, a lot of times I like to not give forces because you don't need to. It's a little more conceptually difficult if all you're given is, let's say, a displacement. So let's say that your initial displacement is 10 meters. Let's solve a first problem, part A, where we're being told that, let's say, the force is tripled. And so if you wanted, you could actually use the Tuesday video, the video from yesterday that I put together to answer this question, but let's actually just use this simulation again, because there's just a more general way that you could also think about these. So I'm looking at what happens if I triple a force. I have two springs here. I can even just, as long as I have the same spring constant for both, so right now they're both on 200 newtons per meter. That's really important. You can't run this test unless you have some control variables. So if I'm seeing what happens when I do something to the force, I need to make sure that my spring constants are the same, so that's not skewing my results. And I'm looking what happens if I triple my force. So let's apply, let's say, I guess 20 newtons on spring 1, and then I want to triple that force for spring 2, so I should apply 60 newtons on spring B. And let's compare their displacements. So 0.1 meters for spring A, 0.3 for spring B. It looks like when I triple the force, I also triple the displacement. So I'm just going to sort of make a note of that to myself. If I triple the force, I should triple that displacement as well. And then so when I come back to sort of the information that we have for this problem, We started off with 10 meters, and so triple that should be our new 30-meter displacement, which makes sense, sort of. If you pull 3 times as hard on some spring, it should, as long as it's the same spring, be stretched 3 times as much. Now, the other kind of thing that I could ask about these displacements is, what if, instead of changing our force, what if we just switched the spring? So maybe for the same force, what if now our spring constant is cut in half? And so we don't know even what the original spring constant was up here, just like we didn't know what the original force was. But I can run another just like sort of quick thought experiment down here in our simulation that could help me answer this question. So now, since I'm changing the spring constant, I want to keep our force applied the same for spring A and B. And so just sort of arbitrarily, I'll pick 50. You could have this at any value as long as it's the same. In fact, just for no real reason, I want to pick a negative, just to see sort of what those negative forces look like, to remind us that we could have an applied force that's negative or to the left or compressing the spring. And so I've got the same force for A and B. And I want to know what happens if I cut that spring constant in half. So right now my spring constant for A is 200 newtons per meter. So let's cut the spring constant for B down to 100 newtons per meter. That's half of that. And then let's compare their displacements. So we've got 0.25 meters for A. And then when I cut the spring constant in half, now I get 0.5 meters. And so if I'm thinking about when I tripled force, I had to triple the displacement, my sort of note to self here for this change is that if I cut our spring constant in half, my displacement looks like it doubles, right? This 0.5 meter displacement is twice this 0.25 meter displacement. And so if I wanted to answer this question sort of once and for all, then our new displacement would be twice this original 10-meter displacement. And so I would get basically a 20-meter displacement. And so you could run really similar experiments to answer your questions for today's work. You could also, if you want, you can use that Hooke's law equation as a guide for yourself. You can also trust your own intuition, but this is a way that will certainly always work. And while you're getting used to the equations that we're using, while you're getting used to some of those concepts, it's certainly fair to use those simulations as a guide for yourself.